think I'm live. Hey, hello, wonderful people of the internet. Welcome back to another episode of Layos Labs. So today, I don't really know what we're going to do on stream, but I do know this is the last day I can stream until basically mid-September. I don't know when the next stream is going to be, is what I'm trying to say. It might be in mid-September, might not be until November. I don't know. I have no idea. I have absolutely no idea. It depends on a whole bunch of different things. I am going to be actively making video content because once September hits, I've said time and time again that I can't really do much before September because unfortunately I have to take the whole month of August off. And I say unfortunately because I think most people would be very happy to take the month of August off, but I'm one of those people that really likes to get work done. And it really irritates me when I can't do that thing. So the month of August is going to be, I just have to spend the time with my kids. Now, don't get me wrong. I like my kid. He's great. But, it's I just wish I could work too at the same time, but it's just not possible. The entire country of Spain, I think most of Europe, just takes this month off and there's nothing we can do about it. So it's kind of like every year I just kind of dread this month, and it is what it is. So I can't stream in August. My kid's school starts again September 8th, so that's the earliest I can start streaming again. And I've been kind of thinking about what the point is of streaming when I can't really dedicate any time to it, specifically in hours that people can actually watch. I know there are people here watching right now, but it's just kind of I need to explore other avenues of content creation that will allow me to still grow, even though I'm not able to do a live stream for the foreseeable future in a way that is regular. You know what I mean? I can still get work done, but it just has to be irregular because I've got a family. So that it is what it is, Okay, so what are we going to talk about today? By the way, T.S. Just, hello internet, welcome of the back Layos Labs to another episode, wonderful people of another, I messed up, but you know what I mean. Right, so let's go ahead and talk about what we're going to talk about today. So I'm going to press this button. I pressed the wrong button and I think my screen died for a second. I think I'm back. Am I back? I wanted to press, what button did I want to press? This button? That button? No, that button. No, that button. Gosh darn it. I really have been messing up. I've been streaming so irregularly, I don't even remember what buttons to press, what my keybinds are. Okay, so let's talk about what's been happening. So let me open up a new terminal, type in xernalpp, and let's just talk. So, as of a month and a half ago, we were making a video. The video was entitled, what was it? Something like "This is a fractal," right? And it was basically just about the rendering engine that I've made, about the, I don't know, this type of stuff. Hey, Mossy, what's up? I see you in YouTube chat. You're just over here. I hope you're doing okay. I don't want to say personal details on stream, but I hope you're doing okay. Right. So the video is entitled "This is a Fractal." The engine was written in Julia, right? Because I do Julia things like that. I'm in the Julia lab, so it was written in Julia, right? But Julia kept breaking in ways that were just impossible for me to understand, right? I kept getting seg faults. Now the seg faults are kind of fixed. I have a way around them. But even so, it's it's a weird situation where I'm not entirely sure whether I want to continue developing this code base in Julia. So a month and a half ago, I rewrote the entire code base in C, specifically OpenCL. And I want to talk about that experience because honestly, I really enjoyed the experience of rewriting the code in OpenCL in a way that really felt fresh, in a way I have not felt for GPU computing in a very long time. And I know OpenCL is one of the oldest tools in the world for GPU computing, but still, it was it was an enjoyable experience. See you soon. Yeah, I'll see you, Mossy. Okay, so I do want to talk about that experience and what has happened since then. So right now, I have the code working. It is capable of generating, fractals in OpenCL, which means I can basically generate anything that I want to generate. Because again, this engine is not just about generating fractals, it's about creating a general purpose rendering engine that happens to be meshless and uses function systems as a way to create different transformations and create different objects. For example, if I want to create a space example, what I'll do is I'll start by drawing a circle, and then I'll use this circle to draw everything else, the stars in the background, right? And then the planet, and then the rings on the planet, and then maybe an asteroid or something like that out on the outside, right? I can take this circle and I can turn it into all of these different objects, right? And the way this is done is basically while I'm generating the points to this circle, I can then use this very same point and transfer it to all of these other objects, right? And that's the key thing that I can do here that other people can't do, right? So the thing that's interesting about this method is that I can actually render like thousands of objects. I can create topologically weird shapes. I can obviously create standard objects and smear frames. I can do all of this without allocating any data on the GPU. That is to say, the only data that is allocated is for the final output frame, right? And that is pretty cool, I think. I've been thinking about a bunch of different ways in which we could use this in order to render, like, you know, the theoretically highest frames per second value imaginable. Like we could render an entire movie in literally 1 second. There's things like this that I've been thinking about and trying to figure out the appropriate way to pursue this, both research-wise to make it interesting, but also in terms of content creation and stuff like that. So there's a bunch of things here. Now, the core problem with this is the following, right? So how do I generate the circle? Right? Well, a circle can be generated in a bunch of different ways, but one very easy way is with an iterative function system, right? This means you have a function system that you iterate over. And for the circle, it's quite easy. We have two functions, function 1 and function 2. Okay, that's just what I'm going to call it, right? Now, what you do then is you take a single point in space, right? You pass it through either function 1 or function 2 at random, function 1 or function 2. And in the process, what we do is we're essentially taking a point in space, right? And we're either mapping it onto the top half or the bottom half of the circle. And it does this in a like randomly sampled type of way. So basically we're just randomly sampling points in the circle and we end up with a point cloud that is a circle that we can then splat onto screen. It's a relatively straightforward process to do this via an iterative function system. The problem is the following. In order to actually run this on the GPU, one, we have to run this threadwise. That's not too big of a deal. But the other thing that is a big problem is that we have to find a way to compile these functions in some way, shape, or form, right? Cool. Again, not a big deal. In principle, on the CPU, you can pass function pointers in. This should not be difficult, but on the GPU, function pointers don't really exist. I mean, they do, but it's kind of not in the same way that you would expect on the CPU, so you can't pass function pointers in. And of course, we're not just generating circles, we're also generating squares and triangles, each of which have different function systems. And the way in which we're generating these functions is not just simply like, you know, pick function 1, function 2. There could be a whole bunch of other complex things that we're doing in order to make it so that this generation of the circle is as efficient as possible, right? And so on the user side, I want them to see generate circle. And then apply function 1, function 2, function 3, function 4 to that circle in order to generate these shapes in here. Like their thought process and my thought process when I'm creating animations should be in how do I transform this particular object into the objects I want it to become at the end. Like that's what I want, right? Now, this means that, again, these 4 functions need to be compiled, and they need to be passed into a kernel in a way that basically minimizes the compilation time, like minimizes the amount of time we spend waiting for that final function to render and all this kind of stuff, right? So right now, I'm not super worried about runtime. What I'm worried about is that compile time, right? Runtime for this particular method is super quick. Like I literally, if I just benchmark the amount of time it takes to run each individual frame, I can get 5,000 frames per second. Now, this is ignoring the amount of time that it takes to send the data back and forth to the GPU. Obviously, that is a big limiting factor here. But in principle, there's nothing keeping me from creating a very high resolution, high frames per second video output if I were to pass this through Vulkan or something like that. Yeah, not just making the circle into an ellipse, but like weird things, like creating a ring set here, like a topologically non-trivial object, or creating a bunch of stars in space. Like that is taking that object primitive and turning that into 1,000 different object primitives. So like duplication, poking holes in it, again, topologically non-trivial things, creating smears that are non-affine. So the difference between turning a circle into an ellipse, that's an affine transformation because it's literally just, let's say multiply by X and then rotate, right? It's not super hard to do. But creating something like a teardrop, that is a little bit difficult, right? Because now you have to think about, like, there's going to be some sort of weird absolute value function here in order to create that point over there. And then maybe you want there to be like some sort of density in here so that as rays of lights are going through this teardrop shape, it like refracts and reflects in different ways. Like there's a bunch of different things that you could, that are not like, that are very difficult to do just via standard affine maps and stuff like that. Because obviously if I could just put this all into affine maps, then well, we're done. Like there's no question, right? So using a circle as a basic object and altering, yeah, right, to get more details. So like if you want to draw an anime character, you can in principle do that with just a circle, right? Or maybe a square or something like that, right? You should be able to take this circle and turn that into like the hair, for example, something like this. I'm not very good at drawing right now. Maybe you draw the face, which will kind of turn into maybe this, like, how do you do it? Like something like a sharp jaw and then something like this. You know what I'm trying to say? Like the point is that like the circle should be able to transform into all the objects on the scene. Let's say you want to create a bunch, like a huge crowd of people in the distance. Well, then you should be able to transform, like create a set of transformations to create a person. And then you should be able to map that person onto like 1,000 different identical copies of them in the background, right? And so not only are we creating a set of functions, right? It's more like we're creating a set of functions that then chain together into the final rendering thing. So that's the core unique thing that we're doing here that other people are not. It's not just F1 and F2 to generate the circle. It's in the map into all of these other functions, function 1, function 2, function 3, function 4, which then chain together into function 5, function 6, function 7, maybe these guys chain together somehow. Like it's that chain that's the difficult thing. It's the composition of all these functions together into that final pipeline. That's the hard part, right? Something like circle. Yeah, so the circle is it is the object primitive that we're working with, right? Like it's kind of like you use triangles to approximate a mesh. Here we're just using that circle as the first initial object. Again, first approximation of the thing that we're working with, right? And of course, we know from things like the fractal flame algorithm and fractal compression that we can actually make this generator like, we can make generators that are like pretty good, like pretty close approximations to basically any object. We could use like, there are generators to create leaves, for example, and then we wouldn't have to do this weird function composition, except maybe to map it onto like all the leaves on a tree or something like that. Point is, this gives the user a lot of control that they would not ordinarily have. And so the question then becomes a couple of different things. One, how do we get these functions on the GPU? How do we get these functions on the GPU? But the other thing, which is maybe something I didn't really think about as much and I really should have thought about more deeply, is how do users specify these functions? Functions. All right. So let's talk about a bunch of different approaches because I've been working on this problem for a very, very long time and it's super frustrating to me. Something yesterday happened that was very frustrating to me and I want to talk about that in just a second. So it has to do with number 2, right? How many times have you said functions thus far? Oh man, look, when you're dealing with function systems, like that's it. That's all you're doing. You're just talking about functions all the time. Okay, so let's talk about this. So the easiest way I could come up with for people to specify the functions that they want to like throw into this giant general purpose rendering engine, right? How do users figure out which functions to use? Well, they'll write those functions, right? So the user will write, like for example, they'll write, let's say I want to duplicate. I have a bunch of different like examples of this happening in practice that I can show off, but they will write like the specific transformation into the ring, or the specific transformation into the planet that we want, or the smear frame for the comet, or the stars in space. They'll write those functions. So they will write F1 through 7 over here, and I really should use different notation, but they'll write these functions. It's just a question of how do you actually write, like put that into the code, right? And so, you know, you have the kernel, which is the outermost level, right? The kernel. Inside the kernel, you have to have some representation of a point in space. You have to have some representation of the pixels, which are going to be output. You have to have some representation of the colors, right? Cool. This is obvious, right? How do you use this to figure out which functions to use? Wait, maybe I'm misunderstanding the question. Could you rephrase it and try again? Sorry. Like, are you asking how do they know, like, if they want a smear frame, that they're going to have to do, like, x is equal to x times 2 or something like this? Or, yeah, maybe I'm misunderstanding the question. Okay, but yeah, so we have the kernel. In here, we have to have representations of points, pixels, colors, all this kind of stuff. And then we have to have some representation of the object primitive, so let's say circle. And then we have to have some representation of the functions that we're adding onto this circle, right? How you learn what function is a leaf shape function. Oh, that's actually quite intuitive, right? As much as like we can point to and say iterative function systems are kind of complicated, that is a true statement. There actually is a huge amount of research literature in creating that leaf function to begin with, right? So like creating like iterative function systems are incredibly well studied, and there's a whole bunch of like really good generator functions. But luckily, I'm not super focused on these generators, right? I'm more focused on the external things. Like how do I take a circle and I turn it into like a ring? Well, that's super easy, right? All I have to do is say, well, we have some sort of like center location here. That's the origin. And then we just say, okay, we take all of our XY points that are in here, and we just say our point is going to be equal to whatever the point location was before, and then we find its distance r from the center. So then we do plus r or something like this, right? So here's our r value here, which is the distance from the point, and we just kind of like spread it out or something like this. You know what I mean? Like it's quite intuitive because all we're doing is manipulating points in space, and the manipulation of points in space is taught in it's taught in like basic algebra classes. You know what I mean? So like this is something that people know since junior high, and so it should be. Like the first couple times you write it, no doubt it might be a little bit unintuitive, but it has a very like quick learning curve in my mind. At least as someone who has been using it for a while, and am designing it, it feels like it has a very quick learning curve. And again, these are all functions that are like literally just movements in space. So they're like, you know, if you want to move a ball from point here to here, all you have to do is say the point is going to be plus equals like, I don't know, point.x is going to be plus equal 5 or something like this. And this will just shift it over in space. If you want to add a sine wave to it, then you could just do point dot x, you know, plus equals sine of maybe y or something like this, right? And this would mean that like as you move up in y, you have like different variations or something like this. Basically, you can just play around with the functions. And that's another reason why I really like this particular method, because it allows for users to just kind of play around with math in a way that allows for them to see very quick and immediate visual inputs and outputs. It's different than, for example, sine distance fields, where the math is like frankly impossible to understand. This is like very intuitive, visual, like, look, I did x plus 5. That's it. I don't have to think about it, right? Anyway, who said OpenCL? We're getting to the OpenCL part. So let's talk about the different ways in which we can do this. So again, in the kernel, we have the point, we have the pixels, we have the colors, and we have the functions and all this kind of stuff, right? Cool. I also want the ability for people to write multiple functions. So for example, they might also write a square in here, and they might also have different functions associated with the square, right? So how do you do this, right? Well, the easiest way, which is the way that I thought initially, was let's just write a giant function string, right? Just write a giant function string, do all the string parsing myself, and then evaluate that into an expression, right? The reason I thought about this approach first was because, okay, the users are going to be implementing, hey, Marion, by the way, the users are going to be implementing their functions. Again, we don't have to compile those. We can wait for the compilation. They can just pass these in as strings, and then we can like somehow throw those into the kernel at the last minute before compilation, right? That's what I thought. Right? And the reason I thought this is because that's how it works in CUDA. That's how it works in OpenCL. That's how it works in every language. Almost every language that I can think of has the ability to, every C-based API I can think of, has the ability to read in kernels, basically program strings, and use some sort of just-in-time compilation structure at runtime in order to get the results, right? Now, a lot of the times, like CUDA and Metal and all these newer APIs, what they try to do is they try to bundle all that compilation time into the compile time instead of separating out between compile time and runtime. But for me, having the ability to compile everything at runtime was actually an advantage, because it meant that I could stage the compilation. I'd have the compilation of the primary framework, then the compilation of like the user code, and then the running of user code, right? Or the final compilation into its final form or whatever, right? Now, I've done this multiple times before. In fact, I've done this before during my PhD in CUDA, something similar. And again, I did it during my PhD in OpenCL. However, when I started this project a few years ago, I was in the Julia lab at MIT, right? And while I was in the Julia lab, I was like, well, let's use Julia. Why not, you know? And so I went about an adventure of trying to rewrite this code over and over again in Julia. And it took years. I'm not gonna lie, it took years. I'm not gonna say it was my primary project for all that time, but I will say it was the most frustrating project I think I've ever had to do. I started with the string approach, and then evaluating those strings, like meted up parsing them and evaluating them into expressions just did not work for various reasons. A lot of it was due to flakiness, because I've been running on an AMD card, and the AMD pipeline is just a little bit flaky. But like, when it came down to it, like a lot of it was just like, you know, that particular approach doesn't really jive with Julia, right? Cool, fair enough. So I tried a different approach where we tried to read everything in as essentially function arguments, right? The idea was, okay, so the users are going to write their functions. We're going to pass these in as a tuple of functions. Because they're in a tuple, we know the type domain signature, and that way we can generate functions that allow for us to do everything that we need to do. The problem with this approach is it meant that users were not able to really directly interact with the kernel anymore, right? Basically, they were interacting at the Julia level. And when you're writing everything at the Julia level, well, you run into this problem where now everything has to, like, at the end of the day, you want to write a kernel. That's what you want to do. You want to write a kernel, right? And everyone knows that's what it's going to compile down to. So why am I playing this game where like users are writing these functions with this particular set of arguments, we're passing those arguments in, some of those arguments have to be dynamic, some of them don't, and like basically playing this game for Julia to finally generate the function when the user knows what they want to generate. They've already written what they want to generate. There's no reason to do a double compilation process here, right? This type of thing, right? And so I tried with this string parsing, I tried with the generated functions, I tried with then going back to expressions. I tried this like a whole bunch of different ways. Like I think I tried it every way I could think of, right? And then finally, about a month ago, I was on stream, we were doing the visualizations, and I just got fed up. I just couldn't do it anymore. Like I've been on this on again, off again relationship with Julia for years. And this was just finally the last nail in the coffin. It wasn't necessarily like Julia did anything wrong. It's just somehow that interaction between this particular code base and the AMD GPU pipeline in Julia led me to a constant string of segmentation faults. And I was like, I can't do this anymore. Like at least in C, when a segmentation fault happens, I have the tools to analyze why it's happening. And I can probably guarantee that it was my fault that it happened to begin with, right? Whereas in Julia, it's like, I have no idea why this is doing a seg fault. One day, I just open up the terminal, type in using AMD GPU, and it would break. The next day, I do it, and it worked just fine for hours without any problems. And I could not tell why one case was one way and the other case was the other way. So again, a month and a half ago, I said, let's just cut ties for a second, rewrite the code in Julia in OpenCL. And I got to be honest, guys, I knew beforehand that I liked OpenCL, but I really enjoyed this process. I cannot explain why. Like, yeah, okay, it was sticky and I couldn't really stream a lot of it, but just the way in which I'm writing the code in OpenCL is very much intuitive to me. I don't have to think very much about it. So let me show off the code and explain exactly what I'm talking about here. Let's move this over here, and let me just open up CD projects Quibble. Okay. Now we're going to do ls here, and I'm going to cd into. Let me just go into vi examples, and then the most recent one that I wrote, chaos.c. Okay. Now, this is not the cleanest code ever. Just for the record, there's a lot of like weird little nigglings that I want to fix. Okay. And that is to say, there is a lot of room for improvement in the API as it is right now. Keep in mind that literally what I'm doing is I'm taking anything that's written in this in this Quibble format, and I'm doing a whole bunch of manual string parsing on it in order to turn it into something that OpenCL will like. So I'm basically doing a transpilation process. All of this process is basically done by the GPU compiler in Julia, and this is kind of me doing the same thing. So what am I doing? Well, here is kind of the final function string of something that kind of like what I'd want to output, okay? So we're including chaos.qbl and then qb output.qbl. These are two different files. qb is like some sort of generic configuration location for all of your Quibble files that's installed when you run like CMake or whatever. I create a poem, which is essentially the uppermost level, what is a kernel. And then I basically create my shader. My shader has a bunch of pixels in it, and it has some sort of camera. This is literally just, our pixels are like, the 9020 by 1080 image, and the camera is like the way in which we're taking our physical points in space and mapping them onto those pixels, right? I create some points, I create some colors, and then I just output those to screen, just as a very simple outputting it to screen, just to make sure everything's working, right? Then, because I can combine multiple things, I've already outputted to screen. That is to say, I've already made a black canvas, right? And then in the same kernel, without having to relaunch anything or run some different things, I can then also create a new color, and I can create some new points, and I can create Sierpinski chaos. And inside of Sierpinski chaos, I'm going to inject something. So not only am I going to create that final set of points that indicates the Sierpinski triangle, I'm also going to throw in the histogram output RGBA 888. That is to say, I'm going to just output as a histogram to screen at that point in time. It takes in point, color, my camera, and then my points in here. Now, there's a bunch of things here that I want to point out that are actually kind of convenient in ways that I'm not entirely sure if this is the right way to do it, but I like this convenience so much that I'm willing to kind of bend over backwards to make sure this happens, right? So let's take a look at this function call here. So this is called an S call. It's a stanza call, right? The way this is set up is I have verses, stanzas, and the final poem, right? So the verse, essentially what the verse is it's a function that is not compiled. What it does is it just splats all the content into the final kernel, right? A stanza is kind of one level on top of that. What it is it's a verse that specifically can be split up into two, and we can inject other things into it, right? And in this case, we're injecting this into it. Again, at no point am I compiling functions. I'm still just kind of like throwing pieces together into the final kernel, right? Which, for the record, is how it works on the GPU anyway. Anytime you have a function that's in the GPU, it's always inlined, right? And it's kind of done the same way. I'm just making that process a little bit more explicit. But because I've made this more explicit, I can do some tricks here. For example, I'm reading in a point and I'm reading in a color. That's fine, point and color are associated in here, but I'm also doing camera and QPS, right? Which are not actually defined in the stanza, they're defined out here. And I can do this because all the variables are being defined, like we're not defining variables like we don't have this concept of function scoping, right? And so we don't really have to read this in the same way. We can actually use these as if they're global variables. And this again has a bunch of advantages in that, like, now the user doesn't have to think about, oh, what do I have access to with this function, all this kind of stuff. They can just kind of like write and say, okay, I know I'm going to have some sort of canvas that I can write to, and I can just use that in these injected verses that I'm using, right? Again, I'm not saying this is the cleanest way to do things, and I understand there's a lot of issues with this in terms of like code, like correctness and all this kind of stuff, which, you know, we'll have to iron out. But I do like the fact that users can just write this, and this is going to generate a bunch of code in order to generate a Sierpinski triangle, and then inject in the output as we want it to be. Now, keep in mind, the reason we have to do this, specifically for the Sierpinski triangle, is because if we go into VI examples chaos.qbl, and we take a look at the Sierpinski chaos example, what we do here is we go through a number of different iterations. Here's the number of iterations. And in particular, we're splitting the stanza up while we're doing the looping here. It's not like we're generating the Sierpinski triangle and then adding the functions to it. So while the Sierpinski triangle is being generated, we're then moving the points. And again, the reason we want to do this is so we don't have to save data prematurely, right? Again, one of the core advantages of this method is that we only have to save data at the final step when we're actually splatting to screen. There's no situation where we have to keep that data otherwise. So it's essentially a memory-free outside of the output image. I call it memory free, but it's not exactly memory free because, you know, we do have to keep the data for the output image. But outside of that, there is no memory allocated for this method, right? We've kind of thrown all the memory allocations into the function composition pipeline, right? Which is cool. That's really cool, right? So this is kind of the whole thing. Like if we go over here to chaos.c, that's the main thing. The people are able to write these very simple scripts that are relatively readable. Yeah, there's some weird things here, like Quibble Color RGBA 888. That is not a good type name. I will be honest, it's not the best type name, but it's a fine enough type name, right? There's some C-like things that are a little bit annoying, right? Like, you know, and that is one of them, right? Like the fact that I can't just like define the type in a more generic way. I have to specify that it's RGBA 888. But overall, I'm quite happy with that. Then all we have to do is we parse the program. I print the program in this example, and I configure it. The configuration is dependent on your specific use case. So I have two different programs available, two different platforms available. I have my CPU and GPU, and in this case, I'm just running it on the GPU. You can find this with an associated command that's called qbinfo, and it will tell you like what devices and platforms you have available to run on. So then after configuration, all we have to do is define like our pixels, define our camera, and then once we've defined our camera, sorry, the camera definition is here, then we have to set the arguments. Cool. Now, I know what you're thinking. Setting arguments is a bit weird. Like, aren't you going to set the arguments upon launch? That's true, but in some cases, like you could imagine, and I've had cases where I've been using this type of method before, where like actually you have a huge number of different arguments that you're reading in, and it is actually quite nice to be able to just set up the bulk of the arguments up front and only change the arguments you need to on the fly, right? And so this means that we can set like one or two arguments, like for example, in the case where we have like the planet, if we have our meteor kind of like revolving around the planet, we can set that meteor position like every frame, and then we just have to set a single argument every frame, and it's quite intuitive at that stage. Like we've already set the arguments before. There's no reason to reset them on the next kernel launch, right? And so I've gone back and forth, but I do like the fact that we can set the arguments in this way at the end of the day. Then we just run it. We pick which one we're running. We send the data back to the host, and then we write it a file, right? Now, you could argue that there's a lot of bulk here, right? Like, for example, specifying that we want the device to host and all this kind of stuff. I will admit that there is a lot of, like, you know, it's not the cleanest API. There's a lot of things I want to fix up, and a lot of functionality I want to add. There's a lot of backend stuff that I want to fix, like all this kind of stuff, right? But for the most part, it works, and we're able to generate our Sierpinski triangle. Everything's able to run, and importantly, it runs pretty quick. So let me just go ahead and show you that really quick. I'm just going to run oh, do I not have it? Let me just run the last GCC. Oh, I have to CD into examples. That's where it is. So let me run the last GCC. And this is one with timing information. I'll go ahead and show you that one too. So let's go into chaos timings. All I've done here is I've added time. And to be honest, I stole some code. I don't usually steal code, but I did in this case, where literally all I do is I start the clock and I end the clock. After running CL finish, which basically means that everything for this particular command queue is done, right? So that's it. So basically I'm just I'm just seeing how much time it takes to run this particular shader. Now keep in mind, this particular shader, this particular kernel is going to be one of the longer kernels to run. Why? Because I'm launching it with 1920 by 1080 threads. That's actually a lot of threads. I don't usually run with that number of threads. And not only is it running with that number of threads, but I'm also running it 100 steps of this Sierpinski chaos example within each thread. So that means each thread, basically, I'm doing, let's see, 1920 by 1080 is roughly 2 million. So I'm running like 200 million iterations, each of which has to then write to the output screen. So this is generally going to be one of the longest computation, it's on the longer side of the kernels that we will be running, right? In general, what I would do is if I want to do a chaos example, I'd run with a larger number of points and fewer threads, just because the way in which you do iterative function systems in the chaos game requires a longer number of iterations. In fact, I'm throwing away the first 10 iterations because of that fact. But in the case I want to do like something else, I'd run with like a different number of threads depending on what I want to run. So long story short, this is one of the longer kernels that we will have to run. And if I run GCC, chaos timings quibble, and I do a.out with those timings in place, we see that the kernel takes 0.01 seconds, right? So again, this is one of the longer kernels to run, and it's in one of the least efficient methods possible, and it's already running with 100 frames per second, right? And I'm quite happy with that. And if I run time of the entire thing, you see that the entire thing takes 0.3 seconds. So this involves about 200 milliseconds of the compilation of the shader itself, the compilation of the kernel itself, and then also copying back to write to file. So writing to file takes about 0.1 seconds, which is the longest part of the pipeline. And then the compilation of the entire quibble, scribble is the, it takes another like 200 milliseconds. And so when you add it all together, yeah, okay, sure, the kernel's running 0.01 seconds, but the rest of it takes a long time as well. And if we were to just send the data over to Vulkan, then we wouldn't have this problem. And actually, that's a good thing that I want to talk about in the future as well. Because of the way that we're writing this code, it's actually possible to do a lot of frames in advance. So there's a situation here where I could just flood my GPU memory with different frames, because again, the frame is the only thing that's going to be saved at the end of the day. And so I could just like flood my GPU memory with a bunch of frames, maybe do some sort of I don't know, some sort of compression on shared memory to make it so it's a little bit faster. I'm not entirely sure, but I have this idea of maybe being able to generate like basically an entire short film of X minutes. I don't know how long X is, but maybe 3, 5, 10, 20, but generate all the frames of the short film in literally 1 second of render time. And I want to beat, like, I think the best frames per second right now, in terms of like benchmarks that people are able to run with, I think it's like 5,000 frames per second. I think that's like what you want to hit. And I've seen in the Julia benchmarks before, I can hit 5,000 frames per second with normal just runtime variables and stuff like that. So I want to be able to say that I could generate 5,000 frames per second. 5,000 frames, I mean, if you do the math, you do 60 frames per second let's see, 60 seconds per minute. That's gonna be 3,600 frames. So 1 minute is about 3,600 frames. So you do, 2 minutes without really doing anything. You could do 2 minutes of rendering in 1 second. You could get a 2-minute short film in 1 second of render time is what you could do. And I think that'd be pretty cool. The other thing is, obviously building this into a game with like a high FPS would also be really cool, because this can run on my phone, So like this is kind of neat because it works on OpenCL and I can run it on my phone. And actually, it's not too big of a deal to transfer it over to, again, Metal or some other framework. It's entirely possible for me to create a game that launches multi-platform without too much trouble, right? So lots of really big advantages to OpenCL. Now, here's the thing. I said a second ago that I tried to write this code time and time again in Julia, and I just kind of failed. I couldn't figure out how to do it. The problem was last night I did figure out how to do it, and I got really frustrated. So let me go over here to Fable, which is the Julia library, okay? And let me go to, I'm not frustrated, but I was, okay. So I basically gutted the entirety of the old Fable, the old Julia library, and I, literally removing 5,000 lines. Okay, yeah, removing 5,000 lines in order to create a very simple script that runs basically like the C code runs, right? So after writing OpenCL, I could write C-inspired Julia code. Actually, I really like it. It's quite nice. We write the kernel, and we basically do the exact same thing you do in C. The exact same thing. Here's the only difference, and the difference is actually quite, it's actually kind of a big deal, right? So the difference is in the way that we're generating these kind of like functions in which we want to inject other user functions into, right? Is your digital mogul chat GP Diddy serving wisdom with style? I'm sorry. No, not only do you want to, I want to just ban you. I'm sorry, you're done. How do I, why is it not removing this message? That was, I've never just flat out banned someone before. Like even people who do spam, but that's another level of spam right there, man. Okay, so, also, why is it not being deleted? Okay, anyway. So here's what we have to do on the Julia side. I'm going to just go ahead and make this big, see if we can, something like this. Okay, so include from scratch. This is basically the Fable code that we had before. Just like this is a very simple rendition of Fable. That's only like a couple hundred lines, right? I create some function which is output and scale, and this is a function that we want to pass into our final code, right? And so what we do is we write the kernel. This is the same as the poem that we're writing the Quibble Scribble. We create a bunch of different points, A, B, C, D. In this case, I'm creating a square instead of the Sierpinski triangle, but it's the same thing. Okay, good. It won't clear from the screen, but we cannot see it anymore except for your screen share. It's fine. I don't mind it staying there. It wasn't like he said anything like outright wrong. It's just like, seriously, ChatGPT Diddy? Do people think that's funny? Like, is that like what, you know, the youth think is a joke? Am I like so out of touch that I don't really even understand? Like, I don't know. Like, I understand I'm an old guy. I get that. I'm old. I understand. But like, also like, is that supposed to be funny? Like, you know? Okay. So here's the difference, right? So a couple things. One, we can create the square, which is at this point going to be a generated function in Julia, an @generated function. So what this means is when we call this function, it will generate the code that we need. This is exactly what we wanted before. Now, couple limitations to this approach, a lot of limitations to this approach, but the big ones are the following, right? One is that we do actually have to read in all of these from the global scope. Again, or from the one level higher scope. I don't like that, but I also don't mind it too much. I understand that it's more proper to do that. So I understand that I'm the one that am probably wrong about the way that I did it before. So then we read in point color A, square color B, square color C, square color D, square color whatever. And then we read in the function, and then we read the arguments into the function, G2, and then Y scale is equal to whatever we want, right? Okay, so let me just be very clear about what we did here, right? What we did is we basically wrapped all of the code that we want to inject into a separate user function, right? And that's this function in here. And then when we call the function, what we're doing is we're specifically calling the function with a set of arguments here. So 2, Y scale, etc. Right? What this does is it means that our function call here is now just a huge string of different arguments, which is kind of difficult to parse. Like even now, I don't really know how I'm supposed to like space it to make it readable and stuff like that, which I don't like. I think it's less clean. I think it's less elegant. On the other hand, it now works in Julia, right? In a way that I had not been able to get it to work for literally years. And because the AMD issue with the segfaults have been fixed, now the Julia version works as well, in a way that's like, I don't know, I like it better. I like this fact that users are directly writing kernels. They can literally just run square. They can inject the code in as they need to. It's kind of fine. The problem is, as I started thinking about how the Julia code will scale, it does not scale very well because we're reliant on users writing specifically Julia functions to be called in particular ways. So when they're writing these Julia functions, first of all, they have to write them with a specific number of arguments and specific keyword arguments in order to make it so they can even run in this way. Like we have to tell users, you have to write these functions in this way, which I don't like. I don't like telling people you have to express yourself in this way. I think that's, you know, it's bound to run into issues, right? The other issue is that like, let's say you're doing this thing that I said before, this example with like a huge number of different functions. Well, in the C code, you know, this looks like this. Journal, we do circle, you know, and then we have the arguments for the circle, right? Which will be like maybe radius, location, something like this. We open it up and we say, what do we want to do with the circle? Well, we want to do planet stuff. Then we want to output. Then we want to do star stuff. Then we want to output. Then we want to do, I don't know, ring stuff. And then we want to output, right? You get it? Like it's relatively easy to say, okay, this is what it's going to look like on the inside of the code. In the Julia code, what ends up happening is you're going to have a function. And this function, so you're going to call circle. And then we have radius, location. And then we have G, which is a function that we want to call. And then we're going to do planet stuff. Star stuff. Ring stuff. You see what I'm trying to say, and then potentially keyword arguments associated with them, right? And so what I'm trying to say here is like, between the two of them, this one to me is quite readable. Like you say, okay, we're going to do this, and inside this, we're going to do planet stuff, star stuff, ring stuff, output. But the Julia just is not, right? Because we have the circle arguments, then we have the function arguments, and those function arguments are composed of a bunch of mini functions inside of it. So we have one function, two function, three function, then a bunch of keyword arguments associated with that as well. You could argue that there are some keyword arguments that could be shared between different functions, and that could be helpful in this particular case. But it's just, I then also have to write a separate function, which is G, and G takes in all the args that you need, and it basically does, this stuff, right? So then this is in a separate location as well. And so as you're reading the kernel, now you have to think to yourself, okay, but what is this, like, what is this actually doing? You know what I mean? Like, it's just much harder to read on the Julia side. So why am I bringing this up? Because now working in Julia, and I have it also working in OpenCL, and there's like a level of me that, like, after spending years of time trying to get this to work in Julia, like, I'm a bit frustrated that the solution ended up being like 5,000 lines less than what I had originally written. After rewriting this and rewriting, like, literally, if you look at the development of Fable, like, here, let me just go up here to the top, and let me just go, I think that's the button I want to press, and let me do Insights, and let me go to Contributors. I'm not going to sit here and argue that, like, this is my most developed code base ever, but, this is 22,000 lines added, 15,000 lines, taken away, all purely written by me. I didn't copy people's code, obviously, but also this is additional stuff. Like, I worked with kernel abstractions to get this to work. I worked with GPU arrays to get this to work. I did so much stuff in the Julia ecosystem to get this to work, right? So it's not just this code, it's also all the other code. And to find that I can remove like 99% of my code base, and it works better than it did before just because I'm doing things in a different way. Like, on the one hand, okay, it's kind of nice to see that, like, I know that you get blind spots when you're writing code, right? Like, if you only write Julia code, you're going to write code that looks like Julia code, no matter what language you go to, right? And that biases you. It blinds you to ways other people would write code. I see this all the time when people transition from MATLAB code to other languages. The way you write MATLAB code is fundamentally different than the way you write Python code, which is fundamentally different than the way you write C code. And this is why it's nice to be a polyglot and have multiple languages that you know, so that as you're writing code in one language, you can then transition to another language, and that transition is smooth, right? And not only is it smooth, you can cover for those blind spots that you have gotten because you're so used to writing code in a particular way, right? And so I think this is one of the reasons why I found the OpenCL code so refreshing. Yeah, it was a pain. It was all string parsing. I'm not going to argue that this was, like, the most fun code I've ever written, but it was refreshing in that, like, I could just write the code I wanted to write, and I didn't have to think about it, right? I didn't have to think about, like, oh, how's this going to compose with these functions? I didn't have to think about, like, like the complexity that is Julia. I was just like, look, all I'm doing is writing an OpenCL kernel. So I just want the easiest possible way to write this OpenCL kernel that allows for me to expand upon it in the future, right? That's it. That's what I'm doing. And in doing that process, it allowed me to then rewrite the Julia code in a way that I couldn't before, right? So now the question is, do I continue writing the code in Julia, or do I continue writing the code in C, right? Versus C. Like, it just brought up this whole thing, because if you guys remember, like a year ago, months ago, 2 years ago, my entire history on this channel with this particular code base has been questioning, should I continue writing it in Julia or should I write it in C? Now I have two codes, both of them are working in Julia and C. So let me just go ahead and show you the code that is working in Julia, right? We know that the code in C takes about 0.01 seconds to run, to do the kernel launch and to do the kernel run. So let's do the same thing in Julia. Let's cd into projects, fable.jl, ls here. No, I'm going to make some claims that are not exactly true. I did what I could in order to make these this to be like an apples-to-apples comparison. That is to say, I'm trying to write the same code in both languages, but there's some things that you just can't help when you're transitioning from one language to another. Like, for example, Julia naturally has a lot of float 64s and int 64s and stuff like that, whereas C and OpenCL does not. It typically does 32-bit precision, or 8-bit precision when it can get away with it, right? And so, like, for example, the output image was in RGBA in Julia, and I rewrote RGBA so that it used uint8 values instead of using float 32 values, just to make sure that we're writing the same amount of data. This is things that I did to try to keep it close as possible, to try to keep the two things as close as possible. So let me just go ahead and take a look at that. So let's cd into temp, ls here, and let me go into vi, rewrite, no, I think it's, yeah, rewrite example.jl. Okay. So here's a kernel, same thing I wrote before. I am going to remove this bit in here, and we're going to do the generated function, because they end up being the same speed between trying a macro approach, which is what I tried this morning, and trying the generated function approach. They're roughly the same speed. But I was trying the macro approach because this is closer to what I actually wanted, in that you can have like a begin and end statement, which allows you to emulate the C behavior, which is what I prefer in this particular case. But it's just macros are way more annoying to use, and they don't quite work the way I want them to work, blah, blah, blah. Anyway, okay. So we have 100 time steps. We're running everything, and keep in mind, again, the output is uint8, which is the same as C. So let me just go ahead and I guess just run this code. So I'm going to open up a new terminal, and we are going to make it as big as possible. And let's move this down here. Okay, so we're going to cd into projects, fable.jl, ls here. We're going to cd into temp, and I'm going to run Julia --project. Now I'm going to do include. Forgot to comment out at the end. Oh, I might have. Yes, you're right. Thank you. Okay, so we're going to go here, include, and we're going to include rewrite example. I think it's going to work. I'm not sure. Hey, Julian, what's up? Okay, so, oh, that's because I need to just do rewrite example. There we go. Okay. I'm going to do, oh, yeah, I need to include, I think I need to, what did I forget to do? From scratch.jl. Fable RGBA is not defined in main. Okay, give me a second. I got to do a little bit of debugging apparently. So vi from scratch, and there should be a Fable RGBA. There might not be actually. There, apparently I didn't define this in the way I thought I defined it. Give me 1 second to just define struct Fable RGBA, and I'll just define it here. It doesn't really matter too much. It's as long as it's in the global scope, it's fine. Okay, so now we're going to include this bad boy, and we're going to do the rewrite example. Okay, so now we have function main, and what I'm going to do now is do using AMD GPU. And I actually want to do one thing too. I want to do an at time here, using AMD GPU, okay? Again, this is a bit of an unfair comparison, but I don't really know the best way to do this. So that took 0.75 seconds. Keep in mind, that is twice as long as the total runtime of the previous code base that I just ran. Twice as long as the total runtime of the C code that I just ran. Just using AMD GPU. Next, what I'm going to do is, I think I can just do AMD GPU.atTime main, I believe, with the array type rock array, and I think this is going to work. Give it a second, and it will run. Okay. Now I'm not, in this case, I'm not benchmarking the amount of time it takes to output to image. I'm not saving that out. What did you do this? What did I do? I did something stupid. Call to convert. Oh, I did something dumb, didn't I? What did I do that was dumb? I swear this is working just before stream, and then I think I kind of borked it somehow. I must have, right? Maybe my definition of pixels is wrong. Let me try that really quick. Let's go into VI rewrite example, G, and let's look at pixels. Yeah, my definition of pixels is wrong here because I was using float 32. So we do pixels here, and let's grab this bad boy. D $, paste in there. Are you using source control? Like version control? Yes. What is source control version control, or am I just too old to understand? Include rewrite example. Let's try that again. AMD GPU at time main. Yeah, of course. Yeah, I'm using version control. Okay, so that took 3 seconds. Let me run it again. I don't know why you're taking so long. That took a lot of time. I must have done something dumb here. I know I did something dumb. What did I do? I think it's because I specified that this is an array. Yeah, it needs to be specifically a rock array. So array type. Let's try that again, include, and now let's try that again. Okay, this is kind of, I think, what I'm expecting. So it took 1 second, run it again, 0.03 seconds, 0.04 seconds, something like this. Again, this is not outputting to file. All right, so this isn't doing like the long part of writing to file. So let me just go ahead and add that in as well. So we get an apples to apples comparison of basically the whole runtime. Okay, let's try that again. AMD GPU at time. So the whole runtime again for the C code. This was done in 0. Okay, I did something stupid. I can't output this to file because of various reasons. I'm sorry about that. I can't output it to file because I need to convert the RGBA of uint8 into RGBA of float 32. Okay, I'm sorry. I should have done this before stream. But you can trust me in that it takes 0.1 seconds to write out to screen, okay? So let's go back here, and let's just go back here and just return the pixels. Cool. Write this. Go back over here, include. Try it one more time. Takes 0.03 seconds, okay? Now, I did one more thing just to really like highlight the amount of time this is taking. So what I'm going to do now is I'm just going to copy all of this code in here. I'm going to define array type is equal to rock array. And then I'm just going to copy all the code. And I'm going to put it up into here, right there, paste it there. And now what I want to do is AMD GPU at time a second function that I created that's called meh, which literally is just launching the kernel and then doing kernel abstractions dot synchronize or dot synchronize. All this is doing is launching the kernel and then waiting for the kernel to finish, and that's it. And this way I can get a benchmark of the amount of time it's taking for me just to launch the kernel and finish execution, right? So we go here at time meh, it's taking 0.3 seconds, right? So 0.03 seconds, right? So 0.03 seconds is 3 times longer than the amount of time it took to run in C. So let's just go and write this down really quick. So Julia took 0.03 seconds per frame, let's say, and C took 0.01 seconds per frame. Okay, let's put some types in here as well. Okay, now there was actually like, it's kind of hard to do the benchmarking here. It's hard to do an apples to apples comparison. I understand that. There's like a lot of things I probably could have done in Julia to speed it up, because if we look at the runtime here, okay, it doesn't say any of the amount of time was spent in garbage collection. But there's like a lot of allocations that I probably didn't need. I don't know where those allocations are coming from. They're somewhere from within the kernel abstractions API. Fine. There's a lot of ways I could probably improve the Julia code if I kept at it. But the fact is, at this point in time, the C code is 3 times faster than the Julia code for just running a single frame. This is the difference between 100 frames per second with this visualization in C and 30 frames per second with this code in Julia, right? That's a big difference. You know, that's a big difference. If you were playing a game and it suddenly froze and was like a third as fast all of a sudden, that's a big deal, right? And keep in mind, though, that I'm not so worried about the runtimes, because this specific program is going to be about the longest runtime that I could imagine an individual frame is going to be, right? And so, like, in actuality, most of the runtimes are going to be closer to like 0.001 seconds or something like that. It's going to be a lot faster for the actual runtimes of the real code when it's there. This is all just kind of like quick tests to see what I can and can't do with the languages and stuff like that. So back to this discussion about Julia versus C. I'm in this really weird mindset right now, and I have spent a very long time, like I had a video out like a year ago saying breaking up with Julia, but we're still friends. And we talked all about like the problems that I had with Julia at the time. And most of those problems have been fixed, right? The big problems I was having was that Julia was just super flaky. It would keep breaking. I kept getting seg faults when I wasn't supposed to. I could not figure out where these seg faults were coming from. They were somewhere in the LLVM, like, you know, compilation of the AMD stack that I could not introspect, because I just don't know how to look at code at that level. And you could argue that's my fault for not understanding LLVM code, but I would argue, if I, as a Julia user, need to dive down to the LLVM level in order to write what, in my mind, was seemingly simple code at the time, I don't know if that's entirely my fault. You know what I mean? Like, I understand that, like, it would be nice if everyone could introspect the LLVM level code, but I'm not one of those people. I've done it before, and I've learned since how to do it better since then. But I'm not, I hate the fact that I have to do that, you know, like, specifically because at the end of the day, when you're writing GPU code, it doesn't really go down to LLVM anyway. It goes down to NVPTX or maybe SPIR-V if you're doing OpenCL, which is, you know, they're all essentially LLVM flavors, but they're not quite, right? And there's like limitations and things that you can do in SPIR-V that you can't do in LLVM and blah, 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 blah. So long story short, I'm still upset about Julia because of those reasons. So let's talk about the advantages of Julia, right, over C. Let's just entertain this thought for just a second, right? Julia over C. 1, package management. Literally, users can just do add Fable. They can just do add Fable. That's it. And then they get the code base and they can run everything they want to do. That's pretty cool. As long as you're okay running everything in the REPL, it's fine, right? What is another advantage of Julia? You get function package composability. Basically, anything you can write in Julia, you can run in this code base. Well, I say that, but there's actually a lot of limitations simply because we're compiling them down to a kernel. Like, for example, you can't do plotting. You can't do easy, like, printing of lines in kernels. Like, there's a bunch of things that you can't do very easily on the GPU. Just because you're doing this into you're running this in a GPU kernel. But, you know, because you're running this in Julia, you do get basically all the GPU vendors are free. So that means Metal. You get Rock M for AMD. You get CUDA. You get OneAPI. And even OpenCL, right? You get all these for free, right? Which is great, right? So these are all really good advantages for running Julia. Okay, so let's talk about the advantages of C, right? One big advantage is that it is faster, right? At the end of the day, it's faster. And the other thing, which I do hate to say as someone who was in the Julia lab for so long, it's cleaner. It looks nicer. It's easier to write. It's easier to read. It's easier to understand than a lot of the Julia code. I mean, just look at the difference between the two different code bases I just showed you, right? Like here, like, I mean, they're very similar, no doubt. But like, where is it? I want to go into, oh, I think I was in the right file, actually. Here's my kernel, right? Is that my kernel? No, this is my second kernel. Where's my first kernel? Here's my first kernel. Yeah, look, I mean, this mess of function arguments, it's just a pain. It's not easy to read. It's not easy to understand. Parsing that as a human is not easy to do, right? I'm not arguing that C code is necessarily going to be better at the end of the day, because obviously C does have a bit more boilerplate, but I find that the boilerplate is actually helpful to reading code a lot of the time. Like, I like knowing the type of things, and I like the boilerplate allows me to like figure out, oh, what's this doing? Why is it doing? As long as it's properly formatted, I don't really have a problem with it, right? So I'm not going to sit here and say that C is like that much of a win over Julia, but it is kind of nice, right? So let's kind of put this as a half point, right? Like, we'll not say it's like really that much cleaner, but it is, you know, reasonably cleaner. Another big benefit is that like everything is in C. So this means that I can write a game, you know, if I want to. I'm not saying I do, but I could. The engine, there's no reason why it can't be fast enough to output into a real-time game that you can play. I mean, my GPU is a 6700 XT. Like, it's not the fastest GPU. It's been around for years now. Pretty much anybody, if I can run it, you could probably run it too. And again, it actually runs faster on my phone, right? Because of the way the silicon is soldered together. So this is a situation where like, I can make a game with this thing if I wanted to, whereas I could not do that in Julia because I can't execute, or I can't write to an executable, right? That's a big problem, right? Other big advantages of C is that like people know C. They don't know Julia, right? I could more easily convince someone to write C code than Julia code, I think. Maybe I'm wrong, and this is where I actually want your guys' opinion. Like, if you guys had to write C code, would you do it? I guess is the question. I mean, the answer is obviously there are a large number of people who are already doing this. Like, again, because it's C, you can use your FFI, foreign function interface, in pretty much any language. Julia, Python, Rust, whatever you want. Pretty much any of these languages can call the C code just fine, right? And so maybe just the kernel itself is... maybe just the kernel itself is written in C, and then you run it in these other languages or something like that. But still, it's you know, the way I've written these Quibble scribbles, it is itself a different language. Like, you have keyword arguments that you're able to run. You have include, so you can include other files if you want. It's very, very similar to a scripting language. And in fact, that's another big advantage of C, and that like it's already a scripting language. And so if I want to develop this into a scripting language, so you never have to interact with C at all, I can do that, right? So I can turn this. I can turn it into a scripting language where literally you'll just run Quibble, file.qbl, and you never have to think about C. This is actually, it's not even a far extension from what I have right now. It would take a few weeks, but I could do that, right? In such a way that you never have to think about C. It's literally its own language, right? And these are really big advantages of C. The disadvantages are that it's C, right? C over Julia. The disadvantages are that it's C. Right? In that C, you have a lot of memory management that you have to deal with. And like, let's just face it, the amount of code that I have to maintain in Julia is like under 1,000 lines once I rewrite it in the way that I want. And the amount of code that I have to maintain in C is, I don't remember, but it's much more than that. Let me do Quibble. Let me see how many lines of code I have right now. Insights, contributors. I think it's like 15,000 right now, I think. A lot of that, though, is not my code. A lot of that is just STPI images, which is like 10,000 lines in and of itself, right? So right now it's at 17,000 lines. So there's about 5,000 lines of C code that I actually have to maintain. You could probably compile it into a dynamic library in C2 and use it from wherever. Yeah, this is what I'm currently doing. So it's currently compiled into a .so file that you can just call. Like that's how the C code works, right? So let me just open that up as well. Let me do it over here. Control D, CD project squibble examples. ls here, vi chaos.c. Like it's easy. Like just include quibble and then you're off to the races. And this C code is not hard to write. You know, like it's I don't know. It's pretty easy. C is my first language. After that, I learned Java and Python. Python is comfortable. Java confuses me. You can get me to write C all day though. There are new alternatives with great C API. Yeah, that's I think what I'm kind of pointing at here. Like. The main reason I want to use Julia is in part because I am so used to the language. It's what I've been using for years. I'm in the Julia lab at MIT. Like I should be able to get this to work in Julia. And now I know I can get this to work in Julia. But let's say I want to make a game in Julia. What do I have to do? Well, the current code is not going to work, right? And there's a bunch of different reasons why the current code is not going to work, right? So in Julia, I can technically output the code to OpenCL, but that's going to take some time and effort. It's not going to be easy, but I can technically get it to OpenCL. Why do I want it to go to OpenCL? Because you have interoperability between OpenCL and Vulkan, right? Whereas you don't necessarily have the interoperability with these other APIs. Like for example, I'd have to do a completely different framework for Metal as opposed to RockM, CUDA, OneAPI, and all this kind of stuff. Whereas if I want to make a game that the majority of people can play, I can do that right now with OpenCL. All I have to do is take the current code that I'm running and just pipe that into Vulkan. Like literally they have the ability to pass pointers from one, like to without transferring memory. I can just take what I've computed in OpenCL and just throw it onto Vulkan so that we can do a real-time visualization, right? I mean, the .so can be loaded, for instance, Python and MATLAB too, so easy for those people too. Yeah, the only problem is that this particular code is itself a scripting language, and that scripting language isn't a different... So like, people who are writing Julia code don't want to interface with another language for this particular project. That's why I'm kind of like iffy about this, right? Because like at the end of the day, like, here, let me just... Yeah, like at the end of the day, what I'm asking people to write is essentially this code here, right? And it's going to be a lot cleaner in the future, obviously. I actually really like this code. Like, I've always wanted a code that is essentially like a modern take on C, and that's what we have here. We have the ability to use keyword arguments. I didn't show that off, but we have the ability to use keyword arguments. Let's go back into scribbles, tests, and then examples.qbl. So like we have the ability to use keyword arguments in both verses and stanzas. So you can, you can minimize the number of arguments that you're reading in. There's just a bunch of different things that you can do here that you can't necessarily do as easily in C or other languages, right? Or specifically C. So like it is a modern take on C that is just in time compiled by OpenCL. I like that. There's a couple things that I didn't quite get right. Like for example, comment checking isn't quite how I want it to be, and there's stuff like that. Another point, some people don't like package managers anymore due to possible vulnerabilities. Oh, really? Could you tell me more about that? I have not heard this before. I mean, like, I always thought that people really liked, like, for example, the Julia package manager. What's the vulnerability? That people are just going to download stupid code? Isn't that a vulnerability anyway? Like, yeah, what is the vulnerability? Like, what's the problem? Okay, so, yeah, long story short, the advantage of this particular code is that you can literally just write C. You can literally just write C code if you want, or you can write separate Quibble code, and you can just compile this all into a single function, and it works. Yeah, again, there's a lot of really cool things that we could do here. Like, for example, I could, like, in order to turn this into its own scripting language, it's actually not that difficult, and it would take a couple weeks. And I don't know, I'm quite happy with this and the way it looks and the way it reads. Have you tried setting up fuzzing? I have not yet. No, the tests are still very, like, the code is still what I would call bubblegum code. You know, like the phrase when people say, like, it's held together by, like, duct tape and bubblegum. Like, that's where we're at. Like, I wouldn't necessarily call it spaghetti code, but there's a lot of code duplication where it doesn't need to be, and there's just a lot of, like, things that I want to clean up right now. So it's not yet at the stage where I'm like really spending a lot of time, like, dedicated, doing a lot of dedicated tests and stuff like that. Okay. So, right, that's where we're at. I have OpenCL code that I really like. I have Julia code that I kind of like, and I'm willing to go back to Julia if there is a good reason, but I can't find that good reason, right? The way you're talking about this, and I haven't been talking about this, I don't understand why you're even thinking about this still again. See, here's the thing. Like, when you're in I was gonna like relate this to a toxic relationship, but I don't want to do that because of a couple reasons. I don't believe my relationship with Julia is toxic, and second of all, I don't know why the creators of Julia named it after like a girl's name. So then all of a sudden, when you say stuff like this, it becomes a joke that you didn't mean it to be a joke. Like you can be in a toxic relationship with MATLAB, for example, but like it's just the main reason is because okay, here's the main reason I'm considering Julia. It's hype. That's why it's hype. Writing your code in Julia is hype, right? Why? Because nobody has graphics code in Julia. This is one of the first kinds. And to say that you can do something that is not easy to do in other languages, like you can do something that is uniquely Julian here, it gets a lot of people on board in such a way that like you are encouraging people to use the language in a way they hadn't before. Like it pushes Julia into new boundaries, this type of thing. Renamed to Karen. You wanted me to rename my own library into Karen? I could. That would actually be kind of funny. It is hype, like no doubt. Like that's actually probably the main reason. It's just I know the Julia people. I work in the Julia lab. If I have questions about like what I can and cannot do with Julia, I know the people to ask, right? And I can very easily get people excited about this project in Julia, right? More than that, Julia has better tooling than C, right? Like, you know, sure, my specific quibble scribble, easy to read, easy to write. But like, what if you want to do something weird? Like, for example, I brought up, like, let's say you want to do audio visualization, right? Well, audio visualization, yeah, there are toolkits in C. No doubt there are toolkits in C. But like, it's just easier to use audio I/O in Julia. You can just do add audio I/O. You don't have to think about make files. You don't have to think about CMake, none of that, right? You just use it, right? And there's a lot of these advantages that come with using Julia that you don't have in C. Like overall building applications in Julia, though you can't create an executable, is easier in a sense. Like because you don't have to think about, again, like the CMake script and all this kind of stuff, right? Like there's just a lot of really good advantages to writing it in Julia. But another advantage to C is, again, it runs on my phone. So like I can just write my code like outdoors on a weekend without thinking about it, you know? Like, again, advantages and disadvantages. OpenCL is quite useful for a lot of reasons, but like, you know, it doesn't work on all laptops, for example. You know, there's still some places it doesn't run, whereas Julia probably will run in those places. Okay, so anyway, that's kind of like my thoughts as of like right now. I've been streaming for about an hour, which is a good amount of time to, I think, have this discussion. I think the long story short, I've had this discussion time and time again, and every single time I have this discussion, I just somehow lean away from Julia. Yesterday, when I was talking about this on Discord, I thought Julia was faster because I was doing my benchmarks wrong. I forgot to synchronize the back end, which, you know, I always tell people to do, but somehow I just wasn't thinking about it at the time. And so, like, you know, there's a bunch of different things as to why I thought Julia was advantageous here and there are a whole bunch of advantages, but at the end of the day, it looks syntactically dirtier in Julia, right? Join the Rust side. I've thought about Rust. It's just that, like, Rusticle is not bad. There's a possibility that I could do this in, like, I just had to rewrite everything in Rust, and I don't want to do that. Like, I like the C, I like the Julia, I don't want to jump into another pot, you know? Like, it's kind of where I'm at. Plus, like, the GPU capabilities in Julia, again, the GPU capabilities in Rust, again, Rusticle, pretty good, but I know the utilities in Julia are great, right? And so, like, if I'm hopping into a GPU computing language, just gonna stick with Julia, you know? Like, that's how it's gonna be. It's a useful tool. I interface with it in Python a lot for critical sections. Yeah. I mean, the fact is that, like, we've been needing a good metaprogramming framework for GPU code for a very long time. And, like, that's exactly what Quibble is. It is just a very simple, straightforward metaprogramming framework for GPU computation. That's what it is, right? Switch to Lisp and Emacs. I'm not using Emacs. I thought about Lisp. Maybe Lisp. Okay. Good, but that's actually kind of all my thoughts. I realized that this particular stream, specifically on Julia, was titled like OpenCL, I like it, which is true. It is true, but I did want to like bring in context here. Like my personal experience with OpenCL has always been like, OpenCL has always been like kind of a savior for me. I don't exactly know how to explain that. Like, but in my PhD, you know, I was writing code in CUDA, and the CUDA code was great, but then at some point I needed my lab mates to interface with the code, and they didn't know CUDA, so I couldn't tell them to write the CUDA kernel. They don't even know how to compile things in C, you know? So what I had to give them was a way to very easily write the PDE they want to solve, and then just do all the parsing on my end, and that was something I could easily do in OpenCL, whereas it wasn't impossible to do in CUDA. You know, CUDA allows for you to do such things, but it was harder, right? And so OpenCL is always like that one package, that one language, whatever you want to call it, framework, I don't know, but it's that one thing that whenever I'm struggling with a particular language, I can always go to OpenCL and it's always pretty good, and I'm always pretty happy with it, right? My philosophy is use the tools as right for the job, don't choose a religion. Yeah, but the thing is, I'm not entirely sure. I wrote this such that C has more points here, and that is true, but like, you know, we're kind of not weighing how strong package management is and package composability. These are incredibly useful things that like you just have access to in Julia, right? Like the ability to just like add in different packages to your project is something that you can't do very easily in C. And so like, if I'm thinking about workflows, there's a lot of workflows I could imagine where you do actually want to do this in Julia, right? And it is fundamentally easier in Julia, right? I think that's exactly my problem. Like, I have, at this point in time, yes, I've contributed to kernel abstractions in Julia. I've contributed to the Julia GPU ecosystem in such a way that, like, I do have biases, definitely. But you could also argue that I have experience here, whereas other developers don't, right? And so this isn't just like, you know, I'm not just like a Julia user. It's like I'm like, I wouldn't say I'm a Julia developer either, like, because I'm not necessarily that deep into the ecosystem, but like, I've contributed, right, in such a way that like the Julia ecosystem is better off because of what I've done, you know, and in such a way that I deeply know Julia, in such a way that I don't deeply know C. Like just the other day, I was using CMake wrong and I didn't even understand how or why I was using it incorrectly, but I was, you know, and it's one of those things that I don't know because it's been so long since I used these tools. I kind of forgot how to do all this kind of stuff in C, you know. Trying to unbreak packages in R is a nightmare. Yeah, it is, yeah. Anyway, so long story short, when it comes to programming languages on the GPU, like I'm just going to kind of come out and say it. For this particular problem, OpenCL is a great tool. Julia could also be a great tool, but there's two reasons why I think I'm going to stick with C at the end of this conversation. One is it's working in C. I don't want to think about this anymore, guys. I've spent so long writing and rewriting this code base. I want to get stuff out there. That's what I want to do. I want to finally make stuff with this package, and I want to just stop thinking about this, right? Sure, okay, maybe there's somebody who could write this in a way that's faster and more efficient using some metaprogramming tools in C++ or something. I'm sure there's some metaprogramming tool in Rust that allows you to do this better. I don't care. Like, it's fine. It is working in C. It's exactly what I want it to be. And now I can finally get to actually doing animations and making stuff with it. So I do want to talk a little bit about what that looks like. And I want to go back to what I said at the start of today's stream. I don't know how many people are here. Not so many people. By the way, For Loop and Bash, thanks for following, really appreciate it. Maybe you should take like a year's ban on yourself, even considering switching languages again, so free up all the mental energy. Yeah, I mean, that's what I did with Julia, right? Like, okay, I want to talk about something. So let's talk about streaming. I'm not streaming in August. I'm just not. I'm not streaming in August. I'm so sorry. I can't. It's not that I don't want to. I do want to. I do enjoy streaming, but I just can't. I can't do it. There is no time that I will have available to stream in August, and I won't have that time until September 8th, which is when my kid goes back to school, right? Basically, he's off, and the entire country of Spain, I don't know, maybe the entire continent of Europe just takes off this month, and there's nothing we can do about it. I just have to take that time off. Now, that doesn't mean I'm not going to get any work done. I actually do have a lot of stuff that I'm going to be bringing along with me while I'm taking care of my kid. Obviously, I will be taking care of my kid. There's no question. I'm not going to be a bad parent. You know, obviously, I enjoy hanging out with my kid, but I also enjoy working. And so I'm going to be bringing a notebook, and I'm going to be getting work done. It's just going to have to be more pen and paper stuff. I actually have a really cool video planned for the stuff that I'm going to be making in that month and probably afterwards as well that I think people are going to really like. I'm really excited for. But that brings me into the next thing is, what are we doing when I get back? What are we doing when I get back from the August break? And the answer is, I don't know. I don't know what streams will come in, if I will be streaming or if I will be mainly making YouTube content. But I've got a bunch of ideas and things that I want to do. So I'm just going to list that out. Take care of yourself too. No work allowed on this continent during those weeks. Yeah, I like working. I don't know how to put it, but like, there's just something about like, I don't know, like, you know, when it comes to video games, like, there's something about playing a video game that just makes me feel bad. Yeah, I don't know what it is. I just like when you're playing a video game, like let's play a Digimon World is a game that I get miserably addicted to every now and again. Like, just I can't help it. I play Digimon World. Like, especially when I'm incredibly stressed, I would just play that game. I cannot explain why. It's like the Chow Garden except better. You know what I mean? Like, a lot of people will say like Digimon and Pokemon are the same, but I'm like, no. Like, you don't understand. Like, you know, like Digimon, like you raise a single Digimon and you put so much time and effort into it, and then, you know, it's like happy and like hugging you and all this. Anyway, long story short, I get really into this game. But after playing playing it for an hour, I feel sick. Like, I can't explain it. I just feel sick to my stomach because I feel like I wasted that time, you know? After working, I get that same pleasure that I get while playing a video game, but afterwards I feel like, hey, I did something useful, and my brain's constantly turning and I can think about things, and like, I don't feel drained after doing work in the same way I feel drained after like playing a video game. Reading a book is kind of one of those things that it's 50-50. Reading papers is always very nice for me, but reading books, sometimes it depends on the book, you know, like it depends on, it really, like recently I've been getting into narrative poetry, which I quite like. Long story short, what I'm trying to say is that work to me is also a release in such a way that like I enjoy working more than I enjoy not working, you know, in general. And I'm finding myself as a parent constantly frustrated because I don't have the time to work. And I know that sounds bad because, you know, there's that quote that like nobody dies wanting to do more work or something like this. You know, they always want to spend more time with their family. I don't know who said this and I butchered the quote, but you guys know what I mean, right? Like, clearly people enjoy hanging out with their family and friends, and it's a very important thing. But like, I find a lot of fulfillment in work right now, and I want to be able to like make this a thing. So in September, my plan is, when I can, probably not until mid-September, September 15th, because again, my kid has to go to school on the 8th and I'm going to need some ramp up time. I'm going to hit it hard, like as hard as I possibly can. I'm going to hit these projects. November is going to be a bit stressful, and next year is going to be a bit stressful because we have some big events planned, but like in life, but I plan to have a lot of stuff coming out, right? I hope you don't become a workaholic. Man, we are well past the workaholic stage in my life. I want to become I want to go back to the workaholic stage. You know, like back when I was at OIST, like I was working 24/7 and I loved it, you know? Anyway, long story short, like it depends on who you are and what you like and don't like in life. Okay, so I'm not streaming in August. I want to, where am I? I want to hit it hard in September, right? That's what I want to do. So here are my current plans, guys. One, I want a video that, this is a fractal. To be honest, guys, I don't know if I'm going to actually make this video or not. I keep going back and forth with this particular video. The idea is that I want to describe the rendering engine to people on my channel as both a way to update them as to what I've been doing, why it's been taking so long, all this kind of stuff, and as a way to introduce new research. There will hopefully be a paper coming along this as well that I'm submitting to, well, the same journal that SIGGRAPH is in. So it's the, why can't I not think of the name? It's computer graphics. For Pete's sake, I can't remember the name in this but there's a paper that I'm also writing, and I would like this to come out around the same time as this is a fractal. To get this done, there's actually a couple things that I need to do. One is I need to do composability with like sign distance fields, which is something I know a lot of people really care about. Like I know people on this channel have talked about sign distance field as well. And so it's really cool. Like I'd like to be able to show that composability and utility there. There's like text rendering and stuff like that, and like a few other things. But like, you know, long story short, there's just a lot of like little things I still have to do. I'm just going to put ... here because there's a bunch of little things before like the paper is done and before I feel confident enough to put out this, like, you know, for example, docs is in here, documentation, this kind of stuff. Okay. And so I'm not sure if the video is coming out, but there will be a paper coming out around that time. And hopefully that paper will be used in future work because I've got like some ways in which I want to, like, first of all, I want to speed up the algorithm so it's faster and we can get like the highest possible FPS. But second of all, I have like ideas of moving into like quantum rendering and stuff like this. And there's a lot of really cool stuff there. I'm not sure how much of that I want to stream because like I keep running into this problem where like I want to do really cool stuff and I enjoy doing the really cool stuff. But part of the thing that made the stream work back in the day was that like I would be streaming something that was unrelated to the work I was doing in the office. Right? And so in the office, I was doing my PhD, doing superfluid simulations around a nanofiber. It was fine, right? But on stream, I do all the other stuff. I do finite difference time domain simulations of invisible lenses. I would do, I don't know, just DMRG. I do like all this kind of stuff. Like basically, I'd pick something, I'd learn about it, and I'd do it, right? And I don't really have the time to do that as much as I used to, right? So it's kind of like I don't really know where the stream fits in to a modern workflow for me that will work for people here. I don't know. So this is why I'm like 50-50 on whether I'm going to be streaming. But yeah, so videos coming out. There's another one I want to put out, which I haven't quite figured out the title for. It's either My Addiction or The Boundary. But it's a discussion about like what it feels like to do research and like why I'm so addicted to reading papers and like all this kind of stuff. It's the goal is just make like a really visually like just stunning video, right? As best as I can with the tools that I have, talking about like my own personal life and things like this. And I'm quite excited for that video. I'm hoping that this video comes out around November. Let's say November 1st is what I'm shooting for. And then I want to do something which I do want to stream, which is a 24-hour challenge. I've asked my wife about this before so that she can take care of the kid during this time, where basically I get up in the morning, I write a story, I do like just for an hour or two, I write the story, and then I just spend the rest of my time for that 24 hours animating the story and trying to make the best animation and the best visual possible in that time, right? So that will be another video coming out like November 15th or whenever it comes out or something like that. Yeah, anyway, long story short, like I have these plans for things that I want to do in the future, and I'm really excited for it, and it's all kind of based on this engine. So like, yes, I'm leaving for a month, but hopefully when I come back, things are like, I'm really hitting it hard, and we can like just get a lot of work done. So that's where I'm hoping we'll be in about a month. So again, I do apologize for leaving. I really do. But I have a lot of plans, a lot of things that I'm going to show off. Some of it I will be working on next month, even though I'm not able to stream. And I'm not sure where the stream is going to look like when we come back. It might be that the only thing I'm streaming when we come back is this 24-hour challenge. It might be that I come back every now and again for different things. It really just depends. So this is a bye-bye for now, but I want to come back. I'm just not sure when or how or where or why or all this kind of stuff. So we'll see. Main thing is I just need to start putting out some like really good regular like YouTube content, like putting out some good papers that I'm really happy about. Just like getting this work done that I've been doing, but it's just hard to show off because I've been in the weeds, So like now we're getting results, and the getting results phase is simultaneously like the fun part and the annoying part, because like then you have to like wrap everything up into a final project and all this kind of stuff. So this is where I'm going to end it for now. I've been streaming for about an hour and 20 minutes, which is, it's short for a Leos Lab stream, but I don't really have much more to talk about at this point in time. So I will see you guys next time for the next episode of Leos Labs. There will probably be a video out sometime. It's either going to come out like September or maybe October or November. It's either going to be This is a Fractal or My Addiction. I'm not sure which one. This is a Fractal is nice because it describes the algorithm and is kind of like, where have I been type of thing. But again, I'm just not sure how much people actually want to watch that content. Like I know that math content on YouTube is like what is super popular nowadays, in part because of the Summer Math Exposition and 3 Blue and Brown and all that kind of stuff. It's just that like, I don't know. I've been seeing all of this, like all the technical content right now is like, it's not everybody, but just so many math content creators are just talking about AI, and it's just like, it's so annoying. Like I actually unsubscribed from like 3 or 4 different content creators just because like 2 of the 3 of their past videos were all about AI, and I just couldn't take it anymore. It's like, guys, stop. Just stop. There was one particular content creator who I very much enjoy watching, who put out a video recently about like, just like, basically they created an entire video with AI, which is itself very difficult to do because the tooling is kind of bad. And she said it took her like an entire month of trying to figure out how to do it and all this kind of stuff. I don't doubt that. But like the theme of the video was that AI is going to like destroy the world. And it was based on this like 2027 report where like people are arguing that, we're not ready for super intelligence and we have to do all this kind of stuff. And I'm like, dude, like the 2027 report is basically pseudoscience at this point. I don't know if I want to say her name. I feel like I need to do better than like, if I'm going to shout out a content creator, I want to make sure I shout them out in a positive light. I don't want to shout them out in a negative light. I need to stop doing that. I would like to watch the other videos she put out. So yeah, I've talked about her before when I do talk about stuff that I like about this particular content creator. But I need to stop doing this thing where I drama farm. Like for example, I need to stop talking about Pirate Software. Somehow he comes up and but he comes up because I see him as a foil, and like, I'm afraid of that happening to me. I don't usually talk so much about like the negativity coming around it. You know what I mean? Anyway, so that's it for now. I will see you guys next time for the next episode of Leos Labs. Again, I'm not sure when that's going to be. Don't know. But I will see you next time. Thank you guys so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. I'll see you guys around next time for the next episode of Leos Labs, which will be in the future. Bye-bye.